This is how we're going to live on Mars in 10 minutes. So let's start the timer. Number 10. A low-cost base. Obviously, the first step is to get to Mars, and fortunately for us, SpaceX is in the process of developing a fully reusable launch system that will bring down the price of access to orbit from hundreds of millions to about $1 million per flight. Once we have access to orbit, we can begin assembling our base in space using prefabricated modules manufactured on Earth. These modules would be lightweight yet extremely strong thanks to the use of advanced materials like carbon fiber composites and aluminum. They would then be transported to Mars using in-space tugs or other advanced propulsion systems, maneuvered into position using robotic arms, and then autonomously assembled on the surface of Mars using nanobots. This will ensure that our first Martian base is up and running in no time at all. 9. No air, no problem. Once we arrive at our new home on Mars, we'll need to get to work creating an atmosphere. Mars has an average surface pressure of just 6.4 millibars compared to Earth's 15. The thin atmosphere also lacks oxygen and is mostly made up of carbon dioxide. Fortunately, NASA has already developed several technologies that we can deploy on Mars to create an Earth-like atmosphere. One such technology is the Mars Oxygen In Situ Resource Utilization Experiment, which uses a device called MOXIE to extract oxygen from the Martian atmosphere. MOXIE has already successfully produced breathable oxygen on Mars, generating about 5 grams per hour. We can also use Martian regolith to create artificial soil that can be used to grow plants, trees, and algae, which will produce oxygen as a byproduct of photosynthesis. And lastly, nuclear fusion reactors can be used to generate heat and electricity, which can be used to melt the polar ice caps and release oxygen into the atmosphere. 8. Radiation shielding. Another major challenge we'll face living on Mars is radiation. Mars has no active molten core, meaning it is unable to create a magnetic field that can deflect cosmic rays and solar winds like Earth's magnetic field does. This leaves us vulnerable to dangerous levels of radiation if we don't take precautions. Fortunately, we can use Martian regolith to create radiation shielding. We can either bury our bases underground or create domes over our habitats using 3D printing. Regolith, Martian soil, bricks, or even solidified magma can be used to create strong and durable structures that can withstand the harsh Martian environment. 7. Food, water, and energy. In order to sustain human life on Mars, we'll need to produce food, water, and energy using only resources found on Mars. Fortunately, we've already developed the technology needed to do this. We can use Martian regolith to grow plants by mixing it with a nutrient-rich solution and placing it inside a greenhouse. We can also use microorganisms to break down Martian soil and create a more hospitable environment for plant growth. Water can be extracted from the polar ice caps using solar-powered drills and nuclear-powered steam digesters. This water can then be purified using existing technologies such as reverse osmosis and UV light. Finally, we can use nuclear fusion reactors to provide a reliable source of energy that can power our entire base. 6. Transportation. Getting around Mars will be easy thanks to the development of several innovative transportation technologies. We can use electric vehicles powered by hydrogen fuel cells to travel around our base and other settlements on Mars. These vehicles will be clean, quiet, and efficient, producing only water vapor as a byproduct. For longer journeys across the Martian surface, we can use autonomous rovers that are powered by solar panels. These rovers will be able to carry large payloads and travel long distances without the need for human intervention. We can also use flying vehicles to get around Mars. These vehicles will be powered by jet engines that use supercooled alcohol as fuel, allowing them to fly for extended periods of time to carry heavy loads. 5. Communication. Communication between Earth and Mars will be essential for the success of our Martian colony. Fortunately, we've already made great strides in developing the technology needed to communicate over vast distances. We can use optical laser communication to send and receive data between Earth and Mars. This technology can achieve data rates of up to 200 megabits per second, which is enough to support high-quality video calls. We can also use relay satellites to improve the quality and reliability of our communication network. These satellites will be positioned at key points along the Earth-Mars trajectory, allowing us to communicate with our colony even when Mars is on the far side of the Sun. Number 4. Robots and AI. Robots and artificial intelligence will play a major role in our efforts to establish a human colony on Mars. Robots will be used to perform dangerous and repetitive tasks, freeing up humans to focus on more creative and strategic work. We can use teleoperated rovers to explore and to map the Martian surface, as well as to gather resources and build infrastructure. We can also use autonomous mining robots that are powered by AI to extract valuable minerals and other resources from the Martian crust. In addition, we can use drones to transport goods and materials across the surface of Mars, as well as to provide aerial surveillance and reconnaissance. 3. 3D printing. 3D printing will play a major role in our ability to construct buildings, tools, and other structures on Mars. We can use Martian regolith to create concrete-like materials that can be used to 3D print structures such as walls, pipes, and even furniture. This will eliminate the need to transport building materials from Earth and allow us to construct structures quickly and efficiently using local resources. In addition, we can use 3D printing to create tools and equipment that will make it easier for us to survive and thrive on Mars. For example, we can print replacement parts for our vehicles and other equipment, as well as tools for mining and construction. Number 2. Underground living. While living in above-ground habitats may seem more appealing, there are significant advantages to living underground on Mars. Underground habitats will provide natural radiation shielding, protecting us from harmful cosmic rays and solar winds. In addition, they will offer protection from meteor impacts, dust storms, and other potential hazards of the Martian environment. Living underground will also conserve energy, since we won't need to expend resources maintaining a pressurized and climate-controlled environment. We can use natural caves or create artificial underground habitats using 3D printing and other techniques. These habitats can be designed to simulate the Earth-like environment, including an atmosphere, gravity, and even natural lighting. And finally, number 1. Terraforming. Terraforming Mars will allow us to transform the planet's atmosphere, temperature, and surface to make it more Earth-like. By increasing the atmospheric pressure, introducing oxygen, and reducing carbon dioxide, we can create a breathable atmosphere that humans can survive in without the need for pressurized habitats. We can also warm the planet by using mirrors to reflect sunlight onto the surface, or by placing objects in orbit that will heat the atmosphere through atmospheric drag. By melting the polar ice caps and distributing the water around the planet, we can create a more hospitable environment for life to thrive. Of course, terraforming Mars would be a massive undertaking that would require significant time and resources. But with careful planning and execution, we can create a new home for humanity on the red planet. And that's how we're going to live on Mars in 10 minutes. Do you think we'll ever be able to colonize Mars? Let me know in the comments below. And if you want to learn more about the latest developments in space exploration, be sure to subscribe for more updates. Thanks for watching, and I'll see you next time.